Hello, Namaste everyone. I am Ramnath who would like to present you the series on key learnings from chip development part 14. This is on FinFET and gate all around FET. So here I will be slightly digressing from the RTL to GDS topic and then giving some information on FinFET, why it has been developed, and this is actually developed in University of Berkley, California, and was kind of first deployed in the product Samsung Galaxy S6 in 14 nanometer. Okay, so the three-dimensional FinFET geometry is a key technology inflection that enables chip makers to continue shrinking dimensions and packing more and more components onto a chip. Further technology advancements led to gate-all-around FET. Here only preliminary details are given. For more details, as usual, please visit the references and other related materials available on net. Thank you for learning along with me. Feel free to provide your suggestions. In this slide, the long channel MOS operation in different conditions have been shown here. Okay, so if you observe there is no channel formed because VG is equal to 0, and here also it is slightly greater than 0 but still less than the threshold voltage, so there is no noticeable channel, or actually no channel formed. Actually depletion layer has been observed here, and when VGS is greater than the threshold voltage, the inversion layer has been formed. Okay, and when the VDS is greater than 0 but less than VGS minus VTH, then the channel has formed in a triangular manner, actually trapezoidal. And however, if the VDS is far greater than VGS minus VTH, you can observe that it has formed only up to this. So the inversion layer slightly moved away from the drain region. Okay, this the more details you can find it through several uh, MOS channel operation books or material. Okay, I am not going too much into it now. I'll go into the short channel uh, MOS operation. Basically, what are the effects of them? Before we analyze the FinFETs and other technological advancements happened in VLSI, let us briefly go through what happened and what was the situation in the earlier years. If you see from 1990 onwards up to 2025, the channel lengths became further and further reducing. If you see here, and if you see the other way, the transistor count is slowly increasing. Okay, after certain time, very drastically though. Okay, this is obtained from international technology roadmap for semiconductors. So this is based on Semiconductor Research Corporation. Okay, and by set of experts. So this is their main vision is to give some technology trend for next 10 years also. So here, if you observe carefully, the length, which is the critical feature, is continuously reducing. Because of this, more and more transistors are getting compacted. So maybe I would say everybody know about this one. If you see again, like to achieve this one, R&D costs have to increase so that the technology jump happens, and to ensure that the technology jump is realized, fabrication sites also need to upgrade. So all these things, if you see, there is a cost paid for the research and for the fabrication units as well. In 2008 or 10 sometime, the around 20 nanometer or so, there came a situation wherein uh, the gate, even though gate of a MOSFET, even though it is closed, their short channel effects started popping up. We'll discuss more in detail on short channel effects. And so after this onwards, the uh, technology, gate length and all those things, dimensions need to change in a significant manner so that short channel effects will be reduced. So because the physics uh, played a major role. So if you observe, the gate oxide layer became so thin, it's more close like a few atoms wide. Hence, the controlling of that became very difficult. That is how from here onwards the FinFETs started coming up. And the metal layer types also got changed. That means like multi-patterning and the pitch of the metals and poly pitch, so many things and 3D architectures of the IC. So different places the innovation started popping up, and the difficulties associated with the miniaturization and the short channel effects have been alleviated. So from 2008 onwards, if you observe, the new trend started popping up. This is when, as I mentioned, FinFET and other technology started coming in. So 3D technologies. So here there is a new shift happened. If you observe carefully, there is a difference between commercial node label and physical gate length. These two are two different items. In the earlier technologies, earlier years, if you see the commercial node nanometer and physical gate length are equivalent to nanometer, so they are all closely corresponding. Okay, but once it became here, they stopped corresponding to each other. Okay, so this got shrinking further, but there was no shrinking from this onwards. Okay, so from 2012 onwards, the gate length shrinkage, this is the physical one. So what I mean is, so when the physical gate length is 18 nanometer, the code name given for the commercial node number is 10 nanometer. So this is more like a marketing label. So that means like if it had been a planar transistor, or comparing to my earlier technology, this is equivalent to 10 nanometer. That means like, so how this is derived, that is how this number has been derived. So whatever we are talking about 10 nanometer, 5 nanometer and all, or the commercial node number, node name, and what actually is way different. Physical gate length is still way higher, and because we are using FinFET or gate all around, or different architectures associated with it, multi-patterning in the metals and different possibilities, they are still able to do the transistor design at keeping the gate length higher, and but they are able to see the reduction in a in that means like achieving able to achieve higher performance and more compacting and lesser leakage, all these mainly needed features with by keeping the gate length still higher, and they are able to achieve through different architectures. If you see here, different architectures have been suggested here. So based on all these possibilities, new novel architectures and novel transistor designs, these possibilities and that means like miniaturization has been achieved. We will see now what are the short channel effects that has led to the FinFET and other possible architectures. For many generations, the switching speed and hence the performance of the transistor could be increased by shrinking the gate length and by applying the scaled voltage to improve the channel mobility and hence the performance. However, in a long channel, as we know, in long channel MOSFETs, the gate fully controls the channel. Hence, when gate is turned off, that means like there is absolutely no gate leakage, and there is no drain to source leakage in current. Uh, However, in 20 nanometer and below, as we discussed earlier, the since the dimensions are reducing so much, the transistor performance was affected by the short channel effects. So the short channel effects are mainly attributed to the two physical phenomena, which are the limitation imposed on electron drift characteristics in the channel, and the other one is the modification of the threshold voltage due to shortening channel length. We will discuss in a little bit more about some of the short channel effects. These are the short channel effects: the drain induced barrier lowering, surface scattering, velocity saturation, punch through, and hot electron effect. So briefly we will figure out what these are, and later we will go to the FinFET and GA. Let us understand the drain-induced barrier lowering phenomenon. Here, for the present, we will take the simple long channel PN junction diode. Okay, so here this is a unbiased PN junction. So as you guys know, this is for N-type semiconductor. This is for P-type semiconductor. So why we are discussing about N and P or PN junction is like this is the simple MOS transistor where source, gate, drain, bias, body for the NMOS transistor. Okay, so here if you observe there is N plus region and P region, and here this whole thing is P. So and P and N both diodes exist. That means like N and P, later on P and N. As such, both are all same. These are all back-to-back connected diodes. So here, if you see, this is N-type semiconductor because this is the Fermi level and this is the conduction band of this N-type. And in the N-type semiconductor, conduction band is very close to the Fermi level. Hence, they can easily jump to the conduction band. In the case of P-type semiconductor, as we all know, the Fermi level is very close to the valence band. And in the PN junction, especially when it is unbiased, the Fermi level in the N-type semiconductor and P-type semiconductor align. Earlier, you can think that the Fermi level of N-type semiconductor and Fermi level of P-type semiconductor are not aligned, but in the unbiased PN junctions, both these two are aligned. So the pattern will be somewhat like this. Okay, now we will study the other situation wherein like what would be in a long channel uh, NMOS transistor, how these levels will be. So if you observe, the Fermi level is constant because this is at the moment unbiased, and if you see here, this is same as this level, and here this is very long here because this is a long channel device, and this, since this is a PN, here this is a P, here this is PN, this will be a reverse, hence this will go in this fashion. So you will observe that the if you only, because we are now talking about NMOS transistor, so we will talk about how the conduction band will be, because that is the one which will play a major role, because NMOS is NMOS here determined by the electron flow. So if you observe here, this is the one, if we understand, then, and if we try to see how it changes when it is unbiased and biased, then we have understood when and we don't need to draw the Fermi levels and valence band, how it will be in different scenarios. Okay, they will be automatically adjusted. That is what we can think of. Now, with that understanding, let us understand the short channel NMOS analysis. Okay, if you understand the short channel NMOS here, okay, so this is the these are the conditions of this NMOS, and Vg equal to Vt. That means like it is close to threshold voltage and equal. And if this is the scenario, Vt is greater than Vg and Vg is greater than Vs, then this is the conduction band levels. Okay, because this is the short channel, it is in this fashion. Okay, so here this is the depletion region, and if you observe, this is this has been slightly tilted in this direction. Okay, now if the Vd is far greater than Vg, then the depletion layer pushes towards the source. This is the drain, this is the source, and it pushes towards the source. And hence, if you understand here, this is the barrier before. That means like it is, you can consider that it is somewhat the same as the short long channel NMOS barrier, this one. But if you now, if you observe, because of the drain became larger, drain voltage now has influence on the situation which is closer to the source. Hence, this drain barrier got lowered. Okay, hence now with this reduced thing only, now the electrons can push through the channel. So this is called drain induced. That means like a drain is because of some increased voltage or something, it is inducing the barrier which is going lowered. Okay, this is called drain induced barrier lowering. And in short, so the threshold voltage, it can, you can think that it is getting lowered when the drain becomes higher in the short channel devices. Let me illustrate this drain induced barrier lowering phenomenon through the Mickey Mouse uh, animation. Okay, so here the mouse is here and the cheese is here. So if you observe, it can easily go and eat it. Okay, however, we will consider the next scenario. Okay, so in this scenario, this is the gate. Okay, so now because of the cat Tom, the Jerry has a difficulty in reaching the cheese. That means like when the gate is turned off, assume Tom is doing that. So when the gate is turned off, then there won't be any current happening. So that is what it is. However, now you see that this is the, in the short channel, this is what is happening. So because of this dog presence, what happens is like now the Tom will be able to reach the cheese. So that means like big drain will have an influence at the source, and hence the threshold voltage is reducing, hence the current is passing through because the barrier is getting lowered even though the gate is turned off. Okay, so this will happen in the short channel effects. However, if the dog has been far away, assume, then that means like a long channel device. Then the if the cat had been here, as in the previous case, then Jerry would move to get the cheese. That means like that is the phenomenon in long channel device. Okay, so there is no current in the long channel device when gate is turned off, but in the short channel it is. Let us understand the surface scattering phenomenon, which is one of the short channel effects. Okay, here this is the long channel NMOS device, source, gate and drain and the body. Here assume that there is a VGS is greater than threshold voltage, then inversion layer has been formed, and assume there is a small voltage higher. Here it is shown as VDS equal to 0. Assume VDS is slightly greater than 0. Then the electrons will flow from source to drain. Okay, and there will be and it will be a smooth gliding like flow. Okay, largely you can think of. Okay, however, here also that means like in the short channel we will go a little bit deeper, and we will observe that there are two electric fields, one due to in this direction due to gate, and another thing is in this direction. Okay, so there are two electric fields both in the horizontal and vertical directions, and because of this the electrons will be going, and it since it has to be within this region, channel region, so it will be moving up and down like this. Okay, because once it will be affected by vertical electric field, another time it will be affected by the horizontal electric field. So that is why it will be bumping into these regions and moving. Okay, here what we need to understand is like the this surface is if you observe microscopically, you will understand that this is not a pure smooth surface. It will have so many ripples and hillocks, and hence when the electron touches that part, it gets repulsed. Okay, in the sense like it will get reflected, and this scattering what happens is happening at the surface. So the mobility of the electron is not a smooth function, but it is affected due to the two fields, hence in the especially more predominant in the short channel, hence the mobility gets reduced. Okay, so to get an analogy, think that one uh, person is running in this direction. Okay, from source to destination. Okay, however, think that then this is a wall. Think, then think that there is a huge wind blowing in this direction. Okay, then what happens, the person will be tempted to go in this direction, and assume that this wall is not a pure smooth one, then he will get deflected by it, so his speed will get affected, and this due to scattering phenomenon again. So that is why his speed will be affected, hence the time it takes to reach will also be changing. Let us understand the another phenomenon called velocity saturation. Here the NMOS drain current versus the drain to source voltage is plotted. Here this is the long channel device characteristics. Here the saturation voltage is occurring here, and the drain current is not increasing further even though the drain source voltage is increased. However, in the short channel device here, uh, the saturation is occurring very early, and the drain current is no longer increasing. So the reasons being, here, that means like here these are the preconditions. So so the main reasons for this is like, as you know, the drain current is modeled in MOS device as mu into electric field. E stands for electric field. So this is the drift velocity. Okay, so of the electron. So here, if you observe, when the voltages are increased, that means like higher electric fields, there will be based on the doping levels and all, a critical, especially the short channel devices, a critical value will be reached, after which the drain current plateaus. It doesn't increase, saturates, I mean. So, so this is due to scattering phenomena again. So this is the effect of the scattering phenomenon. However, this is also will lead to reduction in currents, and hence the delays will also be affected, and the transconductance will also get affected. All these other things will start creeping in. Let us consider the other phenomenon, punch through. Here, let us bring back the same short channel scenario wherein Vd is greater than, far greater than Vg, and Vg is greater than Vs. So the depletion layer shown in the gray color is moving towards the source. Okay. For now, let us keep aside the drain induced barrier lowering phenomenon. So now, under, let us, we need to also consider the source, even though it is same as the bias voltage, but however there will be very little depletion layer around it. So now let us consider another scenario wherein the drain voltage is further increased. Then what happens is like the depletion layer will come so close to the source depletion region, source side depletion layer region, and hence the uh, electrons here will punch through and will reach the drain. So that is what is explained here. So in this phenomenon, if it is occurring, that means like the NMOS transistor is having no effect due to the gate voltage. Okay, so the punch through should be avoided. The short channel NMOS device, hot electrons will also be seen if in the cases where drain source voltage is larger. Okay, so this will lead to aging. We will figure out why it will happen. So here, if you observe closely, this is the drain as usual, source, substrate, and gate. Okay, here the gate has the gate, and this has the silicon dioxide. This is the silica, as we know. And when the electrons are moving from source to drain, when the drain source voltage increases further, there is a chance that the sum of the source, these electrons leaving from source, will be able to cross the barrier between the substrate silicon to silicon dioxide. There will be a small barrier. They will be able to break that barrier and go into the silicon dioxide, and they will not be able to return when the drain source voltage is brought back to zero. Not all of them. Okay, only some could be. So this is called, so this is happening because the electrons are becoming uh, very high and getting high velocity, and this high velocity is basically modeled as hot electrons. That means like it is more like the electron velocity is increased at a high temperature, and it is you can think that the velocity of the electron is when it had been a higher temperature, that velocity is now getting to the electron due to the high voltage. So that is why it is called hot electron. Okay, so it is just modeled like that. So these hot electrons, that means like velocity, electrons having higher velocity will be able to penetrate and go into the silicon dioxide, and it will stay there sometimes permanently in the interface oxide. And because now they are changing, what happens is like the CV characteristics of the MOSFET will change, and this will also lead to aging phenomenon. Okay, so that means like it leads to delay degradation. So that means like you can think that this is the hot carrier injection. This is one more phenomenon, and this will happen in the cold temperature. Okay, and this will lead to uh, uh, delay degradation, and even not this is what is happening in the NMOS. Very similarly, even in PMOS transistors, the holes will be able to go through the same thing, and they will also be able to punch through. Only thing is, because the whole mass is larger, hence they will not be able to make so much of an impact. Thus we don't see hot holes. Okay, so these are the phenomenon which will be seen in the short channel devices. Hence, as we have discussed earlier, the channel length is kept same or almost same, and the other phenomenon like device characteristics has been changed, different gate materials have been changed, and sometimes the UV electron, those UV light things have been changed, or the FinFET and gate all around kind of methods will be employed. So those kind of methods are used, and still, and thus they are able to bring performance and leakage degradation they are arresting, and that is how they are able to bring value to the thing without getting involved into the short channel effects. Let us know more about the FinFET device. Here, let us first start with the planar device, which we are all well familiar with. So here, this is the source and this is the drain part, this is the gate. Similar to the, this is what is the planar transistor. But in the case of FinFET here, so there is an extra fin here, and this will be connected to the source, this will be connected to the drain, and this is the gate. Okay, so and in the FinFET, FET stands for field effect transistor, which is same as what is the same as in planar transistor, where here also whatever the field will be controlling, same way in FinFET also it will be controlling. So if you see here, the yellow thing shown here is the gate oxide. This gate oxide is present in three uh, places, and the gate is surrounding the fin, and this is the fin. Okay, this is the fin here, and the oxide is around it. So here you will see one thin oxide going like this, and the gate is all around here. Okay, don't get into that GAA. Here it is, gate is surrounding in three sides. Okay, so if you see here, that means like this gate oxide and another gate oxide, another gate oxide. So there is a thin film here, and this gate will control the uh, channel here in three places. So that is why the leakage current in FinFET is far less than the planar one. Hence, the FinFET can be, with other advantages included, can be work very well compared to the planar devices. So let us consider the fin here, how it came. This is coming from the fish having one fin here. Okay, whatever this fin will do, same thing this is doing, and this gate is this one. Okay, and it has only one fin here shown here, and in the K, and this is shown figuratively in this fashion. Okay, so this is the fin shown here, and it is connected to the source region. This part of the fin is connected to the drain part of the region in between the channel, which is controlled three sides. Okay, and uh, in the case of two fins here, there are two fins here, and this is source, this is also source, that one drain, this one is also drain. So the gate is controlling two fins here, which is similar to this one. Okay, and if you see further how the FinFET, uh, say in 5 nanometer and all, how it is offering better uh, that means like reduced area and reduced power, all these things how it is providing is, so as we told earlier, the technology wise, assume it is 5 nanometer, the actual channel length is 16 nanometer to 20 nanometer. So then how this is offering benefit? That is what we need to see. That means like when the channel length is almost same, that means like channel length is not reducing. That means like actual channel length. The branded name channel length, of course, is 5 nanometer. Assume. Then why we are with that? We are paying so much money for the wafer cost. As you know, wafer cost of 5 nanometer is way higher than of a 28 nanometer or 22 nanometer wafer. Why? So to know about that, we need to know one important point. That is, the transistor channel length is not the only feature that must be patterned. Okay, so there are other dimensions, other in the FinFET, which need to be taken care of in a very specific manner and in a controllable manner. So those dimensions need high resolution. So we need to employ very EUV lithography, which costs in billions of dollars, or say millions of dollars, few $100 million. So if you see earlier, we have known that uh, the channel length is not reducing drastically, but aside to that, there are so many critical parameters like gate length, gate pitch, fin width, fin height, fin pitch, contact size, contact pitch, or metal pitch. All these things are also very key. These are the ones which are making the dimensions of that means like if the device dimensions had been reduced, how much benefit that device would give, we are getting by tweaking these parameters, and hence we are getting the device, that means chip area reduction and power reduction and all that. So if you see that a 5 nanometer process would contain metal one pitch of 30 nanometer and contact to gate pitch as 51 nanometer, fin pitch as 25 to 27 nanometer, like that. So how these dimensions are very important, and they need to be very controllably created. And these will happen because we are employing extreme ultraviolet lithography tools, okay, which are so costly. So hence we will find that all these things are happening with the FinFET technology, and we are seeing the benefits of that. Let us also understand one more thing, why we are paying so much money towards EUV lithography tools in sub-nanometer fabrication. So you as told earlier, the gate pitch and the fin pitch and fin height, the fin width, all these things also play a crucial role, and fabricating them through extreme accuracy so that yield will be high makes a huge difference. Assume that we have created these things using uh, a DUV scanner, which usually employs a 193 nanometer wavelength. Then to print a 30 nanometer feature only by possible through multi-patterning. That means like it needs to create some pattern, then it needs to use multiple masks, sometimes two or three or four masks. That means like, and if there is small misalignment in one mask, then the yield will suffer, and it will impact the chip performance, and hence the customer returns. However, in the recent ones, in the EUV scanner, the wavelength is 13.5. As you guys know, in the diffraction, de Broglie wavelength and all, the wavelength and accuracy are related. Hence, it can create a pattern which are needed in the gate pitch or fin pitch and all in a very accurate manner in one go. It doesn't need multi masks. So this is where the high cost which is given to the EUV is justified, and hence the yield will be higher. So that is why all these things are playing a role in making a smaller size uh, chip and lower power chip. Here we will see different types of the FinFETs. Here this is having a single fin source and drain here, and its uh, other cross-sectional view. As we have discussed earlier, it is shown in the same way in a three-dimensional manner, and this is where three fins are shown. This is the gate, and here four fins are shown with the gate. These how many number of fins, and what should be the types of gate, all these things depend upon the design we are making. Let us consider one more time the single FinFET device shown here, and this is also shown in a much better manner. Here this is the gate, this is the thin oxide, okay, and if you see here, that is shown here in another fashion, and here this is the fin shown here, and this is the gate, this is the gate shown here. And if we see here, as we have mentioned earlier, it is a gate is surrounding the fin in three sides, and this is the channel length here between source to drain. This is the channel length which it is important, and that channel length is shown figuratively here, okay, and the this FinFET device effective width is two times the H fin. This is the height of the fin, so this one, and this is doing it two times. So this is one height, another height, and the thickness of this. So this is the effective width. That is why the dimensions being same, the effective width is getting increased. As you know, drain current depends upon the width of the device. So it is directly proportional, hence you will get a larger current. However, the device leakage current will be reducing. This is the main thing. And this is another view, cross-sectional view, wherein it is shown the fin and other things. Maybe if you are interested, please look into this one more closely. So here is the layout view, and this is an equivalent representation of how it would be in silicon. So this is the TEM view or scan SEM view in some cases, and this is one fin, another fin, and these are the fins here we are talking about. Okay, for representation purpose, I am just comparing this one with this layout view. So this is the fin pitch. Okay, here that is same represented in 3D three-dimensional way, and this is the fin width or fin thickness. Okay, that way is in the earlier picture I have mentioned what will be the thickness, and this is the length of the gate. So this is the length of the gate shown here. So this is the poly gate. Okay, so this is the poly and gate, and these are the source and drain of the fin. They are shown here. Okay, so and this is the TM view. In some cases SEM view or TM view are taken, and this is the fin height. Okay, so like that, please use this go through this one in a little bit more detail, and the references also corresponding to them, so that now you will gain more traction about how all this FinFET will play a role, and it will add uh, benefit in terms of the PPA. Let us connect the schematic view of a MOS configuration in the planar transistor, and later discuss the FinFET view. So here the drain of two MOS transistors are connected together, and if you see here, these are the gates tied here. Okay, and this is the source. Here also is the source in between the drain. Okay, assume that these are the gates of the um, scanning as part of the scanning electron microscope image. Then this belongs to the source, this belongs to the drain, this belongs to the source. Okay, and this is all in the planar transistor. If we go to the FinFET, a very close equivalent of this, then here this part is the source as discussed earlier. Here also source, in between is the drain. Okay, that X corresponds to the contacts. Okay, and here if you observe, so this is the equivalent of this. Here gate 1 and gate 2, but you can consider these two gates are tied together. Okay, so here this is the source region, here this is the source region here. Okay, and this is the drain in between that one. Okay, if you consider here a tri-gate is shown, so that means like this is one gate, another gate, another gate. Okay, so this is the source region, this is the source region. So if you see, these are the FETs. Okay, fins, sorry. Okay, and this gate will divide this fin into this region into, say, source. This one will become the drain. Here again, because of this drain, this becomes the drain. Now it becomes the source. So again this one is the drain, so this one is the gate, so again it will divide it, and these new regions are assigned. So this is the scanning electron microscope, and here also this is one more way of showing it in a 3D manner. And if you see in the recently when I was going through my complex, I just figured out this mesh, iron mesh, they want to use it as part of a grill. So this one, when I saw, it has a very close resemblance to this one. Okay, I'll show you how. So these two are the source regions. Okay, these two are the source regions, and these are the fins. Okay, these fins. Okay, so these are the fins, and these are the gates, the green ones. This one gray, and this is the drain, and these are the source. So in daily life also, if you observe closely, you can see different configurations which you can relate to some of the um, these devices. Yeah. For completion, I want to cover the gate all around device also. If you see here in the FinFET, the gate is covering three sides, but if you see closely in the gate all around device, the gate is surrounding all sides. Hence, as you understood earlier, the leakage current is reduced still further. The yellow is depicting thin oxide. Okay, so that is how. Other than that, the FinFET and gate all around are almost similar. This is the another cross-sectional view. So this is how the gate is playing a very highly controllable manner, controlling the current. And if you see the width, as we have earlier figured out, these whole four will contribute to a width. That means like the width and the thickness, all that means like this thin width of this fin, and or the height of the fin and the thickness, all that will be contributing two times. So this is all about FinFET and gate all around devices.